Next speaker is Abdel. He has a PhD and is an application engineer for formal verification, clock domain crossing, and low power verification. He received his doctorate in formal verification at the University of Freiburg and worked for Synchronous, Germany before joining Mental Graphics. He has over 15 years experience on assertion-based verification, ABV, and supporting major customers in the area of formal verification across Europe. Over to you, Abdel.
Yeah, thank you for the introduction. Today I will talk about why reset domain crossing verification is an emerging requirement to accelerate design to revenue in ASIC development. As you know, today you need a CDC verification solution. This is because CDC paths can introduce metastability, and metastability can heavily affect the functionality of your design. Similar to CDC, metastability, also asynchronous resets can cause metastability. And this is why you have also to consider not only CDC verification, but also reset domain crossing, what we call RDC verification. In this talk, I will go very briefly about how asynchronous resets can cause metastability, then introduce reset metastability verification. I will talk about two aspects of this verification: the static aspect and the dynamic aspect. And we will see that these two aspects are needed to have a complete verification approach. At the end, I will very briefly go over solution in this space, a solution from Mentor. It is a tool called Questa RDC. Now let's first begin with asynchronous reset de-assertion. The de-assertion term means asynchronous reset removal or deactivation. Let's suppose we have a flop with the clock pin CLK, reset pin, synchronous reset pin A reset underscore N, and clock output, flip-flop output Q, and flip-flop input D. Now let's suppose that the removal of this reset pin can occur at any time. In particular, it can also occur in the critical clock time window in the setup and hold time of the clock. And if this happens in this way, then actually the output of the flop can go metastable. And if this is if the output of the flop can go metastable, the rest of the logic, the downstream logic, everything which reads this queue can go also metastable, and you have metastability in your design, which can heavily affect the functionality of your design. This is something that is well understood and is actually addressed during CDC verification. And the simplest way to address this kind of problems is to add synchronizer, what we call reset removal synchronizer. I did this here in this picture. I added 2DFF in green. They are supposed to synchronize this reset here. And as you see here, the output of the synchronizer is used to reset the original flop. Here, the removal or de-assertion of the reset is happening synchronous to the clock, but still the reset is acting as asynchronous, which means it can go, when it's activated, it can be activated at any time asynchronous to the clock. Now let's move to the second type of issues, and let's talk about when asynchronous resets can generate metastability, and when they are asserted. Asserted means activated. So let's suppose we have two flip-flops, flop 1, flop 2. Flop 1 is driving flop 2. We have 2 clocks and 2 reset pins. Further, let's suppose that the reset pins have independent sources. And let's now suppose that we are resetting the first flop before the second flop. And let's see what happened in the second flop here. So what we can see is actually in this diagram is that clock 2 is running, and first flop is first reset is asserted at some time point, and the second reset is asserted a little bit later. What we can see is also because of the assertion of the first reset of the first flop, the output of the first flop is changing, and this change is seen immediately in the input of the second flop, and this is actually seen in the critical time winds of the clock. So this is what does mean here. It means actually we have a change of data at the setup hold time of the clock here. And this is, of course, known to introduce metastability. It means that the second flop here, the output of the second flop here can go metastable and, of course, propagate metastability everywhere in the design. Okay, now let's see if we can simplify this situation if we can prevent metastability to happen. Here is the case where clock 1 and clock 2 are same or synchronous to each other. In that case, even in this case, metastability can still happen in the second flop. If we add de-assertion synchronized of the reset pins, this will not change anything because actually these are de-assertion synchronized and they are not preventing metastability of which is caused by the assertion of the resets. Okay. Another case is actually where the second flop we have a synchronous reset. Even in this case, metastability can also still happen in the second flop. So now let's move. So what we have seen here actually, that is cases which looks like that they are simpler, but nevertheless, metastability can happen. Now let's see how we can avoid metastability. One simple thing is actually, if we assume that we are always resetting the second flop before the first one. So in that case, we are preventing to see changes at the critical time winds of the second clock, and metastability will be not generated. We will be not introduced. If we also isolate the data of the second flop when we are resetting the first flop. So in this case, we are talking about data isolation. So in that case, we can also prevent metastability to happen in the second flop. Another case is actually when we are resetting the first flop, we are preventing the second clock to run. So we are gating the second clock of the second flop. And in this way, we can also prevent metastability to happen. Another actually used methodology or solution is to use Synchronize. For example, if we add a third flop here after the second one, the third flop here will block the metastability of the second flop. So metastability can happen at the second flop, but the third flop will block it and prevent the propagation of metastability in the downstream logic. So these are actually, let's say, these are the solution that designers can use to prevent metastability to happen. And tools will check for this kind of solution if they exist in the RTL and report them to the user if CDC paths are actually safe because you are using clock gating, or safe because you are using data isolation, or are safe because there is kind of reset ordering imposed by the user, or they are safe because you have you are using kind of synchronization. Now, let's talk a little bit about the domains. So we have to keep in mind that we are actually seeing here this metastability happen is because actually we are presenting the first flop before the second flop. So actually this assumption is related to the fact that we are considering these resets have independent sources. This is actually the case of today SOCs. If we look to today's SOCs, we will see a lot of processor cores, DSP cores, IPs, sophisticated interconnection, multiple bridges, advanced power management, which means we have SOCs with very complex clock on reset structures, increased demand of asynchronous resets, and by the end we see that we have to consider resets to be of independent sources, and which means actually we don't have always to assume that they are resets that have to be assumed or to be asserted or de-asserted at the same time. This is something that we have to consider, and this is actually the source of the reset domains. Now, let's look to protocols. In the previous slides, I showed you when to consider CDC path to be safe. So, and this is based on some structure that the tools will detect. Here I'm adding in another component, another requirement for the verification. And for example, if we take the data or the clock gating technology, this will work only if we make sure that when the first flop, when the reset of the first flop is inactive, then the clock gating is actually not active. So this will make sure that this kind of protocol will make sure that the solution that we have is actually correct and working as in the proper way. So we can think about actually for every CDC path that we detect, there is some kind of protocols requirements. They can be written in some assertion like system value assertion or PSL or whatever, and this assertion has to be satisfied by the design, and this assertion can be proven later using formal verification or using simulation. So baseline, so the static part will be the case where we detect the paths and make kind of characterization of what we see is CDC paths that are safe or unsafe. And the dynamic part is actually where we generate the associated protocols for these paths and run these protocols to make sure that these paths are really safe when the protocols are satisfied. Now, let me look to one solution in this area, the Questa reset domain crossing tool. This tool works actually very similar to what we already have as a Questa CDC. This tool read RTL, OPF if we are faced to low power design, Liberty files if they exist, and do kind of checking of the paths. So this is the static part. And of course, we have to add our constraints to tell the tool what resets we have, what reset domains we have, what clocks and clock domains, and which functional modes of the design we are considering. And then the tool will do some kind of analysis and give us results. I will talk about how this is done. And then in the second phase, we generate protocols. These protocols can be forwarded to formal analysis. Formal can take this large number of, usually it's a large number if we have a large design, large number of assertion, prove most of them, and for assertion that are not proven, are failing, or maybe they are explored, not decided by formal, they are forwarded to the simulation. Simulation can run, in the simulation we can run our regression, where we are including assertions that are not proven by the formal tool, and we generate coverage, and this coverage of course can be merged with what we have produced in form. Now this is the complete flow. So the first part is actually about static part, and the second one is actually the dynamic part. So dynamic means we are generating assertion and prove them with formal, or prove them with the simulation, and building a merged database on this. Now let's look to the static part here. The static part of Questa RDC consists of 3 steps. The first one is actually the first step consists of doing the synthesis of the design. This is necessary to understand the clocks, infer the clocks, infer the resets, understand the clock domains and clock reset domains, and to infer for every register the reset domain on the clock domain. So this is this is actually the first step. And then when we are done with this, we start to look for reset integrity checks. We are looking if resets, or looking to the reset tree and doing some kind of checks if the reset tree is used in a consistent way. For example, we are looking if there is gates that has not to be supposed to be used in the reset tree. We can flag that. We are looking if resets are used in the polarity of resets are used in the correct way, always active high and always active low, or if they are mixed. We are using. We are also generating the information if resets are used. Sometimes synchronous, sometimes asynchronous. We also generate information about where glitches can happen, when resets can converge, if pragma reset pragmas are used and are not respected. All these things all this information can be generated and can be accessed by by the verification guy and can be debugged. The third one is actually the most important one. Is actually the check where we looking for the paths, for the reset paths, and classifying these reset paths to safe or unsafe. So we are looking for paths where we can say that these paths are actually safe because the reset ordering. This is a kind of constraint given by the user. The user specify that reset one is actually the assertion of reset one can occur before the reset two, and we take this into account. And when we are looking for the reset paths, and based on this, we can tell, for example, this is actually a safe reset path because the given reset ordering. Or we can also identify the reset, the clock isolation or data isolation. This can also be done automatically, and we are reporting all this to the verification engineer. I'm not covering here this too much, but actually we can also consider OPF and consider low power elements, which add some kind of complexity here for the analysis. So, in summary, today's design have complex reset architecture. We need RDC verification. Simulation will not solve the problem. We need a complete and automated tool. The tool will be used in a static way, but also in a dynamic way. So the static will be generating or telling us what is safe, what is unsafe regarding paths. And the dynamic aspect is actually to prove the associated protocols. I also talked a little bit about Questa RDC, which present a good solution in this space. It's an easy to use, well-defined methodology. For large designs, we have hierarchical flow. Yeah, that is in brief my talk today about reset domain crossing and how to verify metastability caused by asynchronous resets. Thank you for your time. Okay.